Hello students, and welcome to the lesson on free fall equations. And in this video we're going to take a look at the equation for an object that is free falling through space, and we are going to do a problem with this equation. So first let me give you this equation, and it's going to seem a little bit unusual and mysterious at first, but I will explain each part of this. So the equation says S of t equals negative 16t squared plus v0 sub t, this is also pronounced v naught, okay, plus s naught. So just a quick couple of notes here on the pronunciation. V with the little 0 right here is pronounced v naught, like naughty, but without the y, and then s0 is s naught. And let me explain what each of these variables mean. Okay. So this equation is used when you have an object launch directly into the air and you want to figure out its height. Okay. So s of t is the height, okay, also known as the position of an object at any given time. Okay. T is of course time, and this is measured in seconds. V naught is the initial velocity, and I want to make one thing very clear, is the initial vertical velocity. So it's how fast was it going upwards or downwards when the object first started moving. And this is measured in feet per second. And then finally, S naught is the initial position. And again, this is the initial vertical position. And this is measured in feet. Or you can also look at this as the starting height. I forgot to mention one thing earlier up here. S of t, height of the object, this is measured in feet. So this equation works under the following circumstances. First is that it's a free-falling object, meaning that there's, for example, an airplane that's being powered by an engine that is not free-falling, but like a golf ball that's hit directly into the air, that would be considered a free-falling object, because there's no power. Once you hit it, it's sort of floating through the air, and there's no more power added onto it or force added onto it besides the force of gravity. Okay? And this works when we are using feet as units of height, and we are using seconds as unit of time. And there's one more thing I want to explain here, and this is probably the most perplexing thing of all. This is a sort of a magical number. Negative 16 will always be a part of this equation as long as it's in feet, and this just means the force or the acceleration due to gravity. In other words, as soon as an object gets launched into the air, the moment that it is launched, there is a force acting on it, the force of gravity, that's always pulling it down, and it's pulling it down at this rate. And so that hopefully gives you a little bit of a better understanding of this equation. Now let's look at another form of this equation, and you'll probably see both of these. And in fact, I think the second one is what you might see more often. Here's another version of this equation. S of t equals negative 9.8, and sometimes usually 9.81 t squared plus v naught t plus s naught. And if you notice here, this equation and the first equation here, they're identical except for the negative 16 and the negative 9.8. So it's the same thing. Okay, so this equation is same as this other one, as the first equation. Okay. Except height is measured in meters. Okay. And velocity is then measured in meters per second. And so this is basically the metric, using metric units. So this equation uses the imperial units, this equation uses the metric units. And that's all there is for right now to this equation. Deriving this equation is a lot of fun. It is something that's terrific, that can be done at a collegiate level physics classroom or maybe in AP calculus, but at the level of pre-calculus and high school physics, we are not able to derive this equation, so we have to sort of accept that it's true. But if you continue in your academic careers in math or physics, you will certainly get a chance to derive this equation and see where it really comes from. And this equation here is so important because it describes any sort of projectile object that's in the atmosphere that is launched while you're on Earth. Okay, so now we're going to take a look at a problem that applies this equation. So I have this problem here that says from a height of 3 feet, a tennis ball is launched directly upwards. Okay, so directly upwards is a very important part of this problem here, with a velocity of 95 feet per second. Write an equation to model its position above the ground. Find the maximum height of the ball, and then determine how long the ball will stay in the air before it hits the ground. So we've got a few things that we can work with here. And so let me go back to my whiteboard here and just diagram this out. So I have some variables here that I'm working with. So this is the initial height, and this was 3 feet. Okay. And then it says that there was a velocity, the initial velocity was 95 feet per second, and then it was directly upwards. Okay, directly upwards. So we can basically use the free fall equation. Now, there are cases when even if it's not directly upwards, we can still use the free fall equation, but we have to be a little bit more careful about those cases. This problem is a fairly simple one, so we don't, because it's launched directly upwards, so we don't have to think a whole lot about this. If you see that it's launched directly upwards, and it was a tennis ball, so there's no sort of engine or anything that's powering it, we can basically use the free fall equation. And since this is all in feet, we're going to use the negative 16. Okay? If it was in meters, we would use the other equation. So just a reminder, this was negative 16 t squared plus v naught t plus s naught. And now we just have to substitute the values here into our equation. So s of t is equal to negative 16 t squared plus v naught, in this case, is 95 feet. Whoops, I don't need to write the units in here. It's 95 t, and then it had an initial height of 3 feet. So as far as number 1 is concerned, we are done with our equation. Okay. And just a quick sketch here. So this is basically what's happening. You have a tennis ball. Here's the ground. Here's a height of 3 feet, and it's blasted straight up here. Okay, this is a vector with a velocity of 95 feet per second, and again, it's directly upwards. Go straight up. and it's going to go up, but of course gravity is always going to pull on it, so eventually it's going to come back down. And this equation here will tell us what's its height at any particular moment in time. Next, we have a question here that says, find the maximum height of the ball. And so there are several ways that we can do this problem. We want to find max height. So for this case, I'm going to graph height versus time, and then I'm going to find the maximum value. So to do that, I'm going to fire up my TI-8384 graphing calculator. Let's see, we're going to go into mode. I've been working in parametric mode for a while here, but let's go back to function mode for a moment. And let's graph this equation. It's going to be negative 16 t, or x in this case, since my calculator uses x, plus 95 t, or x, plus 3. And then my window, well, let's just think about it here. The x here is really time, so time starts out at, I'm going to make it start a little bit under 0 just so I can get a better view of the graph. And I don't think this thing is going to stay in the air for longer than 10 seconds, so that's a good x max. X min, again, it's going to fly pretty high up there, but I'm going to go, and it starts out at 0, but I'm going to go a little bit under 0 just so I can get a better view of things. And then finally, the maximum height, and this is really just a guess that we're making here. So I'm going to guess that it reaches maybe 100 feet, or no, maybe it reaches like, that seems reasonable. And then, and if I'm wrong, well, I just have to adjust. So hit graph. Oh, and it turns out I am wrong. It goes way above 50 feet. So you can see the graph starting to be drawn here. Okay, so I have to adjust my window now, and I have to make this, let's see, is it done graphing? Let me see my window, please. So the x values are pretty good. So just to be safe, let me go up to like 100. And maybe this will give me the view that I'm looking for. Wow, it's still flying up there, even higher than I expected. So let's try again. And you know, if you're working on this, even the moral here, as you're watching me do this, is that finding a window for a problem like this is it's a bit of an inexact science. It comes with a little bit of experience, and it comes with understanding with the problem that you're working with. So let me try 150. Hopefully this does it. Ah, there it is. And I'd like to graph this on my paper as well, but I'm gonna first go to second, calc, find the maximum here, the fourth item on the list, and just move my cursor. You can see me here pushing the left button. Move my cursor a little bit to the left, move it a little bit to the right, and then taking a good guess on roughly where it's going to land. And so the maximum is about 2.968, so basically 2.97 and 144. Okay, so let me just transfer that graph here onto my paper. And as always, if you solve your equations by graphing, you need to show the graph. If you don't like to solve by graphing, there are certainly algebraic methods to solve this, but graphing is probably the best choice to go. So I know that it has a maximum height of about just under 150. Okay, so I'm gonna go, this is kind of a crude looking graph here, but I'm still gonna make it work. So 50, 100, 150, okay, and this is height in feet. This is time in seconds. And 2, 4, well, 1, 2, 3, 4, 5, 6. And we said that it hit the maximum around 3 seconds. And it was about 144 feet in the air. So, and it starts out here around 3. So it does this, and then it's going to come down. So I know that this maximum point here from my calculator, it tells me that it is it is a 2.97 and about 144.02. So it's approximate. So I've labeled this point here on my graph 2.97, 144.02. So my answer is that the maximum height is approximately 144.02 feet. So it's going to reach that height, and then it's going to start falling back down to earth, to the ground. All right, so I've answered that question. Now let's look at the third question here, which asks us, how long will it stay in the air before hitting the ground? In other words, if we look at this graph, it's really asking us how long. So this here starts out at 3 feet. It reaches its maximum height, and it's going to come down, and it's going to hit the ground right here. So what we're really looking for here is the x-intercept. So let's find the zeros. Second calc, 0. Left bound, well, I'm already on the left side, but I'm going to go a little bit closer just because it's a little bit easier for me to deal with. Enter. Go a little bit to the right, enter, and then bring it back for a guess as close as I can. Okay, so you see this number here, -1e to the -11th. That's just a rounding error, and it's practically 0. And so the x value here is about 5.97. Okay. So if I sketch my graph here, this is 4, 5, 6. This point here is approximately 5.970. So this answers the question, that it will stay in the air for about 5.97 seconds. And so there you have it, a problem with free-falling objects. And we dealt with a fairly simple scenario here of an object that's just launched directly into the air. And we are just basically using the equation that's given to us, substituting in the right values that come from the problem that are given to us, and then using a little bit of our knowledge of parabolas and using our TI-83 graphing calculators to find the max, finding the x-intercepts, and just being able to relate the maximum and the x-intercepts back to the original problem. Okay. In the next video, we're going to talk about, well, what happens if it's not launched directly in the air, if it falls off a cliff, or if it's launched at a slight angle. So what happens in the next video we're going to deal with is what happens if this tennis ball is launched at a slight angle, going this way instead of going straight up. But for right now, we are done. Have a wonderful day or a wonderful evening. If this is the first video, make sure you continue on and watch